Okay, in the last video, we introduced the fundamental theorem of analytic functions, and he gave us a new way to compute path integrals. The usefulness of the theorem really depends on whether or not we can find the primitive of the integrand or not. And then we introduced Goursat's theorem, which gives us a condition to guarantee that there would be a primitive. So this entire video will be dedicated to looking at ideas on how to prove that theorem. Okay, so let's jump right to it. Okay, so just a quick review of what we've done. So the Goursat's theorem tells that the function will have a primitive if you have a simply connected domain and the function is analytic. Then it gives us a precise way of writing down the primitive. The way we're going to prove this is through two theorems. So Moreira's theorem says that as long as you have the path integral of a loop, triangular loop, is equal to 0, then you have a primitive. And Cauchy's theorem tells us that if you're analytic, then the integral around the triangle will be 0. So if it's analytic, it has 0 for triangles. And if you have 0 for triangles, then you have a primitive. So that is the line of argument. So let's look at Moreira's theorem first. Okay, so let's say you have a continuous function f in a simply connected domain. Then the condition that the path integral on a triangular curve is equal to 0 is enough to show that f is a primitive. So let's prove this. So here's the idea. The idea is to first look at the disk. So we want to prove it for any general simply connected domain, but we'll first look at a disk. And the primitive that we're going to propose that works is this guy. So I've written C to Z, but really what I mean is path integral from C to Z with a direct line segment connecting the two. Okay, so what I want to do is show that the derivative of this guy is really the integrand. So that's what I want to prove. So let's look at this. So the derivative is the limit of the difference quotient, like so. And then if we look at there's two path integrals here. So f of z and f of z naught. So if you look at the unit circle, C is the center, Z is some point close by, and Z naught is a point of interest. So we have two path integrals that's close by. Notice that I'm subtracting the path from C to Z naught. So that's equivalent to adding a path integral that's going backwards from Z naught to C. Now we don't have a triangle yet, but we're actually close to having a triangle. We would have a triangle if we also added a path from Z to Z naught. Okay, then we would have a triangle connecting C to Z to Z naught back to C. We don't have that in our integrand yet, but what we could do is we could add and subtract such path. So if we add a path like that and subtracting is the same thing as going the opposite path, right? And this means that this will make a triangle, which will have integral of 0. And what we're left with is the path integral going from Z to Z naught. So that's this in the integrand, in the numerator is equivalent to the path integral from Z naught to Z. But Z and Z naught is very close to each other because we're looking at a limit as z approaches z naught. We can make this close as we like, and we know that function f is continuous. So as it gets closer and closer, the integrand is actually pretty much a constant, right? It's almost the value at z naught, right? So if you look at line segment where f of w is approximated with f of z naught, which it would be better and better approximation as we take the limit, then the integral is well approximated by f of z naught times the difference in the paths, which is z minus z naught. Conveniently, this cancels with the denominator, and we just have that the limit approaches f of z naught. So what did we show? We showed that the difference quotient limit has a limit, and it's equal to f of z naught, which is exactly what we wanted to show. So capital F is the primitive of the function lowercase f. Okay, I hope you're good so far. So we've done it for disk, but is it going to be true for simply connected domain? Well, what we could do is that if you have a complicated path, you could always shrink it down so that it fits in a single disk. Let me show you what I mean by that. This is a really important technique to know, and we're going to come back to this idea. So what we could think about is that, so if you have a simply connected domain, that means that there are no holes. And what we can think of is like a slowly deforming any path gamma so that it shrinks down smaller and smaller continuously until you have a point. So I kind of try to picture this over here, where the gamma, let's say gamma O for, I guess, the outer path, is shrinking down smaller and smaller until you have a dot. And what I want to show is that that as I shrink this curve, the path integral does not change. How can I do that? So what I'm going to do is I'm going to compare gamma I for maybe the inner gamma. And if I shrink it a little bit, the path integral doesn't change. I could do that by kind of breaking up the path in the following way. So what I will do is look at a small loop where part of the path is on the outer path, and there's a path in the inside as well that's on the gamma I. And then there's an intermediate path that connects the outer and the inner path. So I could take a little segment like this, and actually I could do a whole bunch of small path that way. Okay, so what I'm doing is I'm filling up the gap between the outer curve and inner curve with lots of small loops. And let's see how the path integral should compare. Okay, one thing to notice is that between these small loops, okay, so we're going counterclockwise on the outer path and clockwise in the inner path. And on the curves that kind of jump from outer to in and inner to outer, notice that the two nearby loops will cancel out that part of the path, right? So each path that connects the outer to inner part will be traced twice in opposite direction. So if I'm adding up these path integrals, the inner parts, the connecting piece will cancel out, right? So let's see. So let's say I have the path integral for the outer path. And then notice the inner path is now traced backwards. I'm going clockwise instead of counterclockwise. So I'm writing negative to show that I'm going the backwards direction. So this is equal to the sum of the little loops, which I'm going to call gamma k. Okay, so the sum of the small loops is equal to the one big outer curve minus the inner curve. Okay. I will show that these are equal to 0. So if these small curves loops are equal to 0, then that would mean by rearranging terms, if the negative sign will disappear when I move it to the right-hand side of the equation, and we get the path integral for the outer curve and the inner curve is the same. And we can repeat this argument until the curve shrinks down to just a point at any one point in the domain. And the path integral at a point is equal to 0. So that the whole thing would be equal to 0. How are we going to show that the little loops are zeros? Well, okay, what we're going to do the actual proof is for triangles. But what you could do is you could approximate a small loop with a polygon, sorry. And each polygon could be broken up into little triangles. Triangles where the inner edges that I add will cancel out because they're going different directions. So, sorry, that got messy. For example, if I have a polygon square, so if I put in a diagonal, I could break it up into 2 triangles, and so on. And the idea is that any polygon could be broken up into small triangles, each of which I'm going to prove that it's equal to 0 by the following argument that we haven't done yet. And any curves is well approximated by polygon. In fact, that's how we came up with the definition of the path integral, right? That we are approximating with a close by line segments, and that we took the limit. Okay, so that's how we're going to reduce the argument to proving that the analytic function will have 0 path integral in a small triangle. Okay, I hope this is making sense. Okay, before I get there, here's a warm-up computation. That let's say I have any triangle ABC shown there, and here's the formula for a path that kind of traces that triangle. It takes 1 second to go from A to B, then B to C, and then C to A. So 3 seconds total to traverse this path. In the following argument, in the Cauchy's theorem for triangles, I'm gonna prove that if you're analytic, this path integral will be 0. But first, let me prove it for constant function 1 and function z for 2 special cases. I want to do this because I'm going to use this result in the proof of the following for the general analytic function. Okay, it's really not too bad, but it does take some computation. All right, so let's do the path integral for the constant function 1. So if you're taking the integral of the constant function 1, I have to multiply by the derivative of the path. So because these are linear functions, we just have to multiply by the coefficient of the t is going to be the derivative. And all of those are just constants, so you can pull that outside of the integral. You just compute the integral of 1 from 0 to 1 and integral 1 from 1 to 2 and 2 to 3, they're all equal to 1. So we just have the 3 terms of the derivatives and they all cancel out to be 0. So the constant case works out. For the function z, basically we do have to multiply by the derivative gamma prime again. So that's taken outside of the integral, but we're also integrating the z itself. So that's the z with the gamma plugged in. Okay. And it is more complicated integral, but really it's a linear function. So it's not too hard to take the derivative, antiderivative of. We can do that here. So here's are the antiderivatives. Yeah, I forgot the squares here. And then when we plug it in, here's what we have. Okay. Notice that b minus a, b plus a, these are difference of squares. So these simplify to b squared minus a squared, c squared minus b squared, and a squared minus c squared as well. So all of those will cancel out and we'll get 0 again. Okay, so remember this result. I'm gonna call this lemma because we're gonna use it later. Okay, so here's the big part of the theorem. So if you have an analytic function in simply connected domain, and if you have a triangle path, then the path integral is equal to 0. So let's prove it. So everything comes down to this theorem. Okay. All right, so let's do this. So we're gonna make up some notation. So let's say I, capital I, is the modulus of the path integral. And eventually what I want to do is show that this is equal to 0. Okay. And what we're going to do is break up this triangle into smaller and smaller triangles. So any triangle that you draw, you take the midpoint of each of the sides. If you connect them, you get this the symbol that looks like Triforce from Legend of Zelda, or you get 4 smaller triangles. So you have 3 here and 1 in the middle. So this is what we're going to repeatedly do to get smaller and smaller triangles sitting inside of the triangle. Okay, so for now, let's call the smaller triangles gamma 1 through gamma 4. So gamma is the big one, the original triangular path, and gamma 1 through gamma 4 is the smaller triangles, all going counterclockwise. Okay, and notice if I add the path integrals together, I get the original path integral I, because again, the middle parts cancel each other out because it's being traversed twice going in backwards direction. Okay, so we have the original path integral could be rewritten as the sum of 4 smaller subtriangles path integrals. Okay, so because this is sum of 4 smaller triangles, one of those triangles is at least 1/4 the size of the original path integral. Okay, so if I look at the modulus of the original triangle, that is less than or equal to 4 times at least one of those 4 triangles. Let's just choose the one that gives the largest path integral in modulus, and call that gamma m. Okay, so I is less than or equal to 4 times one of those 4 triangles. Just for the ease of notation, I'm going to relabel things. Let's just say instead of gamma m, let's say the integral that gives us the largest modulus is gamma 1. Okay, and then once we focus on one of those 4 triangles, we're going to subdivide further. So we're going to keep subdividing triangles into 4 smaller pieces, pick the one that gives us the largest integral, and then subdivide that into 4 and so on. So we'll get a sequence of smaller and smaller subtriangles where gamma j plus 1 is a subtriangle of the previous one. When I say length, I mean that the perimeter of this triangular path is half of the previous one. That's because, notice how if you look at the triangle, this side of the triangle is subdivided in exactly 1/2 to get side of length of that side. This side is exactly twice as long as this side, and this side is exactly twice as long as this side. And you could do the exact same comparison with each of the 4 other subtriangles as well. So because of the midpoint cuts the length in half, the perimeter of the triangle will decrease by a factor of 1/2 every time you go to a subtriangle. The diameter is the 2 furthest points in a triangle. So in this case, on a triangle, 2 furthest points will be one of the 2 of the 3 vertex of the triangle. And because all the dimensions are being cut in half each time, the diameter also decreases by a factor of 1/2 as well. Okay, and we are choosing the subtriangle that gives us the largest path integral. So each time you can compare that the modulus of the next subtriangle is at least 1/4 of the previous one. Or you could say the previous one is less than or equal to 4 times the next subtriangle. All right, so this is how we're going to subdivide step by step. We can translate this to what this means in terms of the original triangle. So let's do that. So the parameter of the jth subtriangle is 1/2 to the jth power times the perimeter of the original triangle. And same comparison for the diameter. So diameter is 1/2 to the jth power of the original diameter of the triangle. And the size of the original path integral is 4 to the j times jth path integral. Okay. All right. So the next thing I want to do is notice that if you subdivide triangle at a certain point, you're kind of zooming in on a point. So there's a point, unique point Z0 that is contained in every single subtriangle. So you're getting smaller and smaller triangle. It's zooming into a particular point. It's really hard to draw, so it's just a big dot in my picture, but there is a point that it's getting closer and closer to. And part of the hypothesis is that F is analytic. So that's the same thing as saying F is differentiable at that point. Okay, so what does that mean to be differentiable? That means that the difference quotient has a limit, right? So the difference quotient minus the derivative at the Z0 is going towards 0. So they become sufficiently small. So let's just say it's less than some number, some small number epsilon, as long as z is close enough to z naught. Okay. So this is the what we want to use, but I'm going to rewrite it a little bit. What I'm going to do is on this inequality to the left, I'm going to multiply each term by z minus z naught. So z minus z naught disappears off of that fraction. And this constant here, I'm going to multiply by z minus z naught. And on the, I have to also multiply on the right-hand side. So I'm going to have z minus z naught here as well, but inside of opposite value. Okay. All right. And now I'm going to go back to the limit that we have earlier. So what did I show? So as long as you're working with a constant function or the function z, if you integrate over a triangle, you get 0. Okay. What that means is that if you have a 0 integral, you could add that or subtract that into an expression, and it doesn't change the total, right? So we want to look at the modulus of the jth subtriangle. If I add a constant or add z times a constant and integrate, I don't change the result because the contribution for that integral is 0. But what I get by adding that in or subtracting that is that now I have this comparison. In modulus, that expression is less than epsilon times z minus z naught. Okay, so I could replace this by epsilon times z minus z naught. Well, z minus z naught is a variable, right? It changes with z. So depending on where you're on the triangle, this expression changes. But let's just say z is whichever furthest point from z naught so that it gives the largest value. We're going to approximate this with the maximum or the largest value that this expression can take, which is basically exactly the same as the diameter, right? Z minus z naught is the distance from z to z naught. So the largest distance you could be is the diameter of the triangle. It could be less than diameter, but to be safe, we could approximate from above by the diameter. And also I'm using the ML estimate. So that's the maximum of the inside. And I also have to multiply by the length of the path, which is the parameter of the triangle. So we're just going to write that as length of gamma j. Now, both of these, diameter and the parameter length, we can compare it to the original integral. So let's do that. So the size of the original integral I, it's positive because we took the modulus, is less than or equal to 4 to the j times the jth path integral. And I have to go back and show you, but let's see. Compared to the original triangle, the parameter is going to be 1/2 to the jth power, and diameter is going to be 1/2 to the jth power. So both of those combined, you will get 1/4 to the jth power. That's what we have here, times the diameter of the original triangle and parameter of the original triangle. So coincidentally, 4 to the j cancels out. So what do we have? We have that the integral is smaller than epsilon times some diameter times some length. So diameter and length are finite numbers. So if we take epsilon, which was an arbitrary, we could picked up to be as small as we like. And this inequality will always hold. So the only way that could be true is if the size of the original integral I is equal to 0. Okay. There was a lot of steps to this proof, but it's a good thing that this is a recorded video, so you can kind of go back and re-listen to the parts that were confusing, or if I went over too quickly. Please ask questions if you're not sure. And I think I want to end the video here. So see you later.